Let's talk about the one-sample t-test and the t-interval. It's a very good idea to use the one-sample t-test or t-interval when you don't know the population standard deviation sigma. You don't know that a population is distributed normally, so we can't really estimate sigma, the population standard deviation, using the sample standard deviation S, or if the sample size is less than 30, preventing us from reliably estimating sigma using the standard deviation from the sample S. The short version of this is that in general, it's really best to use the t-distribution model when you're doing a one-sample inference of the mean. This is the default. Okay? That's because the t-distribution model is a more general version of the normal distribution model. It's appropriate for both small and large samples. Nearly all statistical models, when you're trying to make an inference about a sample mean, and so you're trying to use a sample mean to say something about a population mean, nearly all modern statistical software will use the t-distribution as a model for the sampling distribution of sample means. Again, that's because the standard normal distribution model, or equivalently the normal distribution model, works best only when the underlying population distribution is known to be normal, the population standard deviation sigma, or the sample size is roughly greater than or equal to 30. Right? The key idea that you should know is that the t-distribution model, it's a probability distribution model. It's a model of the sampling distribution, because keep in mind, we don't normally repeatedly randomly collect samples from a population. We just use these probability distributions to make inferences because we know what these distributions look like based on statistical theory. But the idea is, and also just through simulations, as we've covered in this course, but the basic idea is that we use the t-distribution model as a default because it takes into account that greater level of sampling variability, the uncertainty, especially when we have small sample sizes. So let's talk about the different steps for hypothesis testing. We'll first cover the z-test for a sample mean so you get the idea. Then we'll also cover the t-test. So hypothesis testing, we first state the target population parameters of interest. So we're interested in saying something about the population mean using a sample mean. Right? The target population, we might say, oh, we want to generalize to people in London, or we might want to generalize to people in Ghana. Right? Just think about what your target population is. Then we have these steps for hypothesis testing. You first state the null and alternative hypotheses. You state the significance level alpha, which is typically 0.05. You compute the test statistic z. Okay? With the z-test for a sample mean, it's relatively straightforward to calculate this test statistic z by hand. For other test statistics, we won't ask you to calculate it by hand. Then what you do is you assume the null is true. Right? This is the default approach when we conduct a hypothesis test. You just assume that the null is true. Whatever the claim in the null, that's true. Null means zero, really. It's an empty set. It means nothing's going on. So we assume, hey, the null is true, nothing's going on. Then we see what's going on in the data. And so we can compare the test statistic z with a critical value, or we can compare the p-value based on that test statistic, all right, to some significance level alpha. In either way, we have a decision rule, we make a conclusion, and we state that conclusion and we interpret it. We can also construct a confidence interval. The z-test statistic for one sample z-test. This is where you have one sample from a population and you have a sample mean and you want to say something about a population mean. The z-test is based on the standard normal distribution. That's why it's called a z-test. So it really works best when you have a pretty large sample size, and you know even better if you know something about the population standard deviation. Typically, we won't use the one sample z-test, but it's a good way of understanding what's going on. Most statistical software will use the one sample t-test. The test statistic, the z-test statistic, is simply the sample mean minus the null mean, right, the claimed value of the mean in the population, divided by the standard error of the sample mean. Right? But the standard error is sigma, the population standard deviation, divided by the square root of n. Okay? So this is based on the idea that because of the central limit theorem, we can approximate, we know something about the sampling distribution for the sample mean. It's approximately normal. Right? This is sometimes called a z-test statistic. It's a standardized score. Right? This might look familiar. What it's telling us is telling us how far a sample mean x bar lies from the claimed mean in the population of the null hypothesis. And it's standardized by the standard deviation of the sampling distribution, the standard error of the sample mean. The basic idea is that the more extreme this test statistic, either very positive or very negative, the more inconsistent our data is with our null hypothesis. And when we have really inconsistent values of our z-score from our null, when that's really inconsistent, that implies we should reject the null hypothesis because it's so inconsistent. We should reject it. So we can also conduct a t-test for a sample mean. Okay, this is by far more common. Right? The preliminaries are similar. We state the null alternative in terms of the steps. We state the significance level. We compute the test statistic t. Okay, we're going to use statistical software for this, but has a very similar format as the z-test statistic. It's just based on the t-distribution model, which requires some computation because the t-distribution model changes depending on the degrees of freedom. So we can't just look it up at a table. We really have to use statistical software to compute the test statistic t. Then we assume the null is true, and we again compare this test statistic with a critical value, or we compare a p-value based on this test statistic with some significance level alpha. In either case, we come to a conclusion, and we can also construct a 95% confidence interval. So what does a t-test statistic look like? Right? The t-test statistic for a one-sample t-test in which you're trying to say something about a population mean based on a sample mean, right? It's given by the following form. Okay? Typically, we don't know the population standard deviation, so we use the sample standard deviation as an estimate for that population standard deviation. But you see it's very similar. Right? It's just the sample mean minus the claimed value of the population mean divided by the standard error. The difference is that this test statistic, it lies on a t-distribution with n-1 degrees of freedom, the effective sample size. So interpreting this test statistic can be relatively difficult if you don't have a computer, or if you're not given the output. For this course, we'll give you the output. We don't expect you to use statistical software on the exams. The basic idea, though, is again, this t-test statistic, it tells us how far our sample mean x bar lies from the claimed mean mu naught of the null hypothesis. To put it another way, you can think of this hypothesis testing as doing the following. The null is saying, oh, the sampling distribution is centered on mu naught, right? Well, if that's true, if the sampling distribution of the sample mean is really located in that part of the distribution, if it's really located on mu naught, and we get the sample mean of x bar, how likely is it that we actually got this value of x bar, given the claim is that the sampling distribution is centered on mu naught, right? If it's really unlikely we obtain the sample mean, given that's the assumption about the sampling distribution, that the sampling distribution is centered on mu naught, then we probably should reject that null hypothesis. Right? That's the basic idea of inferential statistics, and that's the basic idea of the t-test statistic as well as the z-test statistic. An alternative, or to really kind of think about this, is go through an example of the one-sample t-test. This is a two-sided test. That's because the alternative is that the claimed value is just not equal to 47. So the null is that the population mean equals 47. The alternative is that the population mean does not equal 47, so we call that a two-sided or two-tailed t-test. It's a one-sample t-test because we're just looking at one sample from a population. And we get this statistical software output. Okay? From this statistical software output, we can reject the null at the alpha 0.05 level. That's because our p-value is 0.03. Right? We reject the null that the mean is equal to 47. So we've covered means, right? One sample z and t-tests for the mean. Well, what happens when we have a proportion? Okay? Categorical data, we often have proportions. In public opinion research, you might say, what are the proportion of people who support a particular social policy? Well, that often is based on a random sample from a population. You want to say, well, is this true? And what can we say about the population proportion? Well, that's what we're going to cover next. Right? There's something to consider when we make inferences about a population proportion based on a sample proportion. Something called the success-failure condition. Okay? So we call our sample proportion p hat and our population proportion p. Right? This is a slight deviation from the convention of Greek letters referring to population parameters. That's just because if you use Greek letters, then the Greek letter would be pi, but pi would refer to the population proportion. Sometimes you see that, but that's a little bit confusing because pi is a very well-known mathematical constant. So when we talk about sample proportions and population proportions, we typically see p hat for the sample proportion and p for the population proportion. Here's the idea, though. Assuming that we calculate our sample proportion from a random sample from a population, the sampling distribution of p hat, it's going to be approximately normal. So it can be approximated by the standard normal distribution model as long as we expect to see at least 10 successes and 10 failures in our sample. So a success or failure is defined as 10 counts in one category and 10 counts in another category. So to put another way, if n is our sample size, right, and p is some population proportion, okay, we'd expect n times p to be greater than or equal to 10 and n times 1 minus p to be greater than or equal to 10 in the population, okay, where n is a sample size and p is the proportion of the population. So this is an assumption. It's called a success-failure condition. It's an assumption because we can't actually observe p. What this really means, though, is that you can see that the success-failure condition is really a function. It's an expected number of counts, in essence, based on successes and failures, or p and 1 minus p. But the idea is that if we have a pretty large sample size, we can be pretty confident that the success-failure condition holds, because even if p is quite low or quite large, we'd expect the counts of successes and failures to be pretty large with a pretty large sample size. So first thing is to check the success-failure condition. You should also check the target population. Make sure, are you generalizing to people in London? Are you generalizing to people in New York? What's your target population? Then what we can do is we can conduct a z-test for a sample proportion. If the success-failure condition holds, we can just model the sampling distribution for a proportion using the standard normal distribution model, which is quite convenient. So we can state the null alternative hypotheses, we select a significance level alpha, then we compute the test statistic z. Right? We assume the null is true, which is equivalent to saying we think the sampling distribution for these sample proportions is centered on that null value. And then based on that, we can compare where our sample proportion is, and we can either reject or fail to reject the null. We do that by comparing this test statistic z with a critical value, or comparing the p-value to some significance level alpha. We can also state a conclusion, and we can also construct a confidence interval based on alpha. The z-test statistic for a sample proportion is simply as follows. Okay, this is sometimes called a z-test statistic for a proportion. Sometimes it's called a z-test statistic. They don't talk about a proportion, but the basic idea is that you take your sample proportion, subtract out the claimed value of the population proportion, and divide by the standard error, where the standard error is typically defined as the claimed value proportion of the population times 1 minus the claimed proportion of the population divided by the sample size, and then you take the square root of it. That's substantively, you could think of it as equivalent to sort of a worst case scenario or a claim about the sampling distribution. Here's the idea, though. This test statistic again tells us how far sample mean, or rather sample proportion, is from the claimed proportion in the population based on the null hypothesis. And again, you can think of the null as saying, we think the sampling distribution is located on p naught. We think it's located on this claimed value. Okay, we have an idea of the standard error. So if that's true, how likely is it that we obtained this sample proportion that we in fact obtained? It's unlikely, given where we think the sampling distribution is located under the null hypothesis, and we can reject that null claim, that null hypothesis. And so at this point, we've covered the basics of inferential statistics in terms of one sample mean and one sample proportion. We've covered the z-test and the t-test. Next, we'll look at what happens and how we can think about comparing groups in terms of proportions and in terms of means.